Hello, it's Keith here, and this is lesson 23 in the platform-specific series of my 6502 assembly programming tutorials. Now, over the last few weeks, we've been looking at how to do palettes on these systems. We're going to move on now, and we're going to start looking at sound. In my tutorials, we create a common driver called Chibi Sound, which allows us to create simple sound effects on all our systems in a common way. Now, the way this works is we pass the accumulator, and the data in the accumulator will select various pitches and various volumes, and also the possibility of noise. And it will work in a roughly similar way on all of the systems. So if we want to make a high-pitched beep or a low-pitched rumble, we can do that in that common way, and that allows all our systems to work the same. Now, this week we're going to look at the Atari 800. We're going to learn how to write the Chibi sound on that system, and then we will see it in action. So how does the Atari 800 and 5200 sound work? Well, they use a device known as the Pokey Chip. This is quite a popular system, and it is quite good. It allows for 4-channel sound, and it also allows for noise quite easily. The ports of the Pokey Chip are memory mapped, so we just write to a memory address to define each of the pitches and volumes of the 4 channels. But there is a slight catch. Now, as I've mentioned before, the Atari 5200 and 800 are basically the same hardware. The Pokey Chip exists on both, but they move the position of the device. So the port we need to write to is different depending on if we're writing for the 800 or the 5200. The data we do write, however, is exactly the same. So here's the Chibi Sound test code. What we're going to do is we're going to load the accumulator with hexadecimal 80, 128. We're going to show that to the screen, and then we're going to call Chibi Sound with that value. We're going to decrease the value, and we're going to keep looping around. Now, the way Chibi Sound works is it uses a single byte, and each of the bits in this byte has a different purpose. The least significant, most 6 bits are the pitch, with lower numbers being higher. The 6th bit is the volume. If it's 1, it's high. If it's 0, then it's low. And the top bit is the noise bit. If it's off, then we make a tone, a square wave usually. And if it's 1, then we make a distortion sound, again with a certain frequency. Now, there is a special case, and that's if all of the bits are 0, then we turn the sound off. So let's hear Chibi Sound actually running. So here you can see that the number is going down, and you can hear the pitch changing accordingly. And when we go below 0, you will go back into the distortion range, and we will hear the pitch again. And you can hear the quieter ones now. So as I say, the bits are all affecting the sound accordingly. Now, this is the 5200 version, but it does work on the 8000 as well, as you can hear now. So how does this work? Well, as I say, this is all just effectively just running this Chibi Sound routine. We've got the code for that just here. We'll have a look at it in a moment. But the important thing to understand is because we need to write to different memory addresses depending on the system we're using, rather than writing data directly to these memory addresses, we're actually using them as Pokey plus offset. So rather than writing to D200 or E800, we're writing to Pokey plus 0. Now, Pokey is defined in our header here, and it's either defined at being E800 or D200, depending on the system we're actually compiling for. And we're using this conditional compilation to select it, and build A5200 and build A80 are defined in my batch file, depending on which one of these I select. So that's how I'm getting around the limitation of having to write for 2 systems that have a different address for the sound chip. Anyway, let's actually look at the code we're using. So, well, let's quickly just have a look at the theory. So we're going to need to use one of these channels. These channels are all equal in their functionality, so it really doesn't matter. We're going to be using channel 1 in this case. Now, we've got 2 bytes that we write to do this. We've got 4 noise bits here. They're effectively kind of like the instrument that we're using. So the different numbers here will make a different kind of sound. So we will need to change that depending on if we want to make a noise or not. We've got volume. So this is how we define how loud we want our sound to be. Of course, we'll need to change this depending on our 1 volume bit. And finally, we've got the frequency here, and this is the pitch of the sound that we want to make. So we're going to need to convert the 6 bits of frequency, the 1 bit of noise, and the 1 bit of volume to work with these bits. So the first thing we're going to do is we're going to see if we're actually turning off the sound chip. Now, if the accumulator is 0 when this routine is called, then we are indeed turning off the sound chip. So we're comparing there just to check and update the flags accordingly. And if the accumulator is 0, we jump to silent here. Now, the way we silence the sound chip is we set all the volume bits to 0. Now coincidentally, we know that the accumulator is 0 at this point, so we just store the accumulator into Pokey plus 1. Pokey plus 1 is of course this here, the audio control for channel 1. We're using channel 1 in all cases, so if we set that to 0, that will just silence everything out. Now the next thing we want to do is check the top bit. Now the top bit is the noise bit, so if this is set, then we need to use a noise effect. If it's not set, then we're using a tone. So the way we do this is we are now defining the bits of both the noise and the volume. Now the volume on the Atari uses 4 bits, but we only have 1 bit for our definition. We've got this 1 bit here, so we're setting the remaining 3 bits to 1, and then we're going to fill in that volume bit just here to make up the 4 bits of the volume so that the volume can either be loud or quiet. Now to make a noise effect, then what we're doing is we're setting these top 4 bits to 0, and that will create a noise. And alternatively, if we're not doing that, because we just skip over to here, but if the noise bit was not set, we jump to here and we're setting 1010. Now this creates basically a square wave, which is a very simple wave that will make a nice sound. Now if I run this sort of spectrum analyzer here, you can see that we've got this kind of wave here, and you can see that the waves were very square then. This is now, again, you can see it's a very square shape, and that's why it's referred to as a square wave. So that's the kind of wave we're making for when we're doing a pitch. Of course the noise is just very random, and that's the alternate one here. So at this point we've now loaded the accumulator with either our noise profile or our tone profile, and we're storing that in ZAS because we're going to need that a little bit later. Now at this point we've altered the accumulator. We're going to restore it in just a moment, but just before we do that, we're going to initialize the sound control. And what we do here is we need to load 0 into Pokey plus 8. Now the sound control here has various options here, but we actually don't need any of them. We just need them all set to 0 here. So we're just doing that now while the accumulator is in that state where we've already altered it. Then we restore the accumulator because we need to get the bits of our definition back. We get the 6 bits of the pitch. We shift them to the left twice, moving them into the most significant positions. And then we store them into Pokey plus 0, which is the frequency of channel 1. So we've now done the frequency as well. Finally, we need to deal with that volume bit and of course get back our instrument selection for the noise bits. So what we do is we take the 1 bit that's available to us here, we then shift it to the right twice, which effectively moves it into this position here, the 4th bit of the volume. We then OR in the noise profile and the 3 volume bits that we defined earlier, and this now defines a correct definition, which we then just store into Pokey plus 1, which is the volume and the noise profile for channel 1. At this point, we've now done everything, and you can see actually we're jumping back to the same position that Silenced used. I've tried to optimize these as much as reasonable to try and make them a little bit smaller to save some memory. So things in this case, we're actually jumping over all of this code here and using this same store definition here to silence the sound chip. But anyway, that's really all it takes to get sound working in a basic way on this sound chip. Of course, if you're wanting to do music, you'd want to use more than just 1 channel. You'd also want to probably experiment with different options with these bits here to try and make some different instruments possibly. And of course, you've got options here with regards to filtering and other effects here. But that's really outside of the scope of what I was looking to do today. In this tutorial, we're just looking to get the basics of sound going, give you some basic examples for your maybe Space Invaders type game with some simple bleeps and bloops. But if you want to do some more complex stuff, you're going to have to really sort of dig into this on your own and look at to take things further. Anyway, I hope you've enjoyed this lesson today. If you have, please like and subscribe because that helps me a lot. And of course, please follow along for later because I'm going to be covering the Atari again in the future. We're going to be looking at sprites later on as well. Anyway, thanks for watching today and goodbye.